Hello, ladies and gentlemen. My name is David Hill, Scientific Director of Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with Analyte Technologies. Our topic today is Strategies for GCMS Method Development. Diane Turner graduated from the University of Warwick in the UK with a Master's in Analytical Chemistry after developing a technique in GC during her research project. After starting her career as an analytical chemist, she established an applications laboratory specializing in GC and GCMS. Since 2005, Diane has been a trainer and consultant in gas chromatography, comprehensive GC, GCMS and related techniques, where she shares her expertise and knowledge working with both instrument manufacturers and end users. Diane is a member of the Royal Society of Chemistry and the British Mass Spectrometry Society, a ChemNet Ambassador and a Women's Enterprise Ambassador. And so, without further ado, I'll turn the presentation over to Diane Turner. Diane?
Many thanks, David, and hello to everybody, and thank you for joining us for this webinar. So, we're running slightly late already, so let's get started straight away. So this webinar today is on strategies for GCMS method development. The first questions when thinking about developing a method are the big questions. So what questions are you trying to answer? Well, as an applications chemist, many times people would bring me a sample and they wouldn't quite know what they wanted to get out of it. So what questions are you trying to answer about your samples? Do you want to do qualitative or quantitative analysis? Do you want to identify unknowns? First of all, can your samples and analytes be analysed by gas chromatography? Or would another technique like liquid chromatography be a better method? Does the GC method give the qualitative or quantitative result at the level necessary to meet your objective? So when you're thinking about developing a method, work backwards. Which are the best detectors, especially if you want to identify unknowns? So something like a mass spectrometer or maybe even an infrared detector might give you those answers. What is the best column phase? The most standard column phase is an NX5, something like a DB5 or an HP5, maybe MS on the end of it if you do have a mass spectrometer. But is there a better stationary phase that can separate your analytes much easier? And how will your analytes be extracted from the sample matrix? So first of all, let's just examine what the sample matrix is. So you may know some information about your sample matrix, or you may not know anything about it. So a sample is made up of analytes. These are the compounds of interest. What are you interested in? Your matrix is the other components we're not interested in, which often is a high concentration, but there may not be any matrix in your sample. And the thing that we really have to worry about is any matrix interferences. So these can interfere with the extraction and the detection of our analytes. So we have to be particularly cautious and, again, have as much knowledge about these matrix interferences as possible. So when you're analysing samples by gas chromatography, your sample could be a solid, or it could be a liquid, or it could be a gas, or it could be something in between. For example, something like honey is not quite a liquid, but it's not quite a solid either. So when we're thinking about the matrix, first of all, is the matrix at high concentration? Can it damage our GCMS system, or could it cause high maintenance? In these cases, we may need to get rid of a lot of that matrix. Are there matrix interferences in there? So, does our matrix require removing through sample preparation, or could we ignore our matrix by using specific detectors, or by thinking about selectivity at each stage of the whole sample analysis? So, selectivity both in the sample introduction, then separation through your analytical column, and again, selectivity at your detector. Or do we need to do some sample preparation? If we do need to do sample preparation, and we've got lots of samples, can the system be an automated sampling or sample introduction method? And this could then aid the removal of the matrix using selective techniques. So, as far as possible, we could want to try and automate our sample preparation. And there's many different instruments and different techniques that can enable us to do that. So Now let's think about our analytes. So our analytes, when looking at in gas chromatography, are organic compounds of interest which are volatile enough to be vaporized and carried by the carrier gas through a GC instrument, usually below 400 degrees C. However, I've analysed analytes up to about 1200 molecular weights, requiring very, very high temperatures on our GC. We can obtain columns now going up to about 480 degrees C. So if we do have very high molecular weight compounds, then again, we can still analyse them using gas chromatography, but we need to think about that in the first place. Also, the analytes that can be analysed by GC do not compose at the temperature required to vaporise the sample. So when we're analysing our sample, we're separating all the components and we're analysing them. Ideally, then, we don't want to have these types of compounds actually in there. So only around 20% of known organic compounds can actually be analysed using gas chromatography. So in other cases, we need to think about other techniques. So also thinking about our analytes, what approximate concentration are these? Are they in the percentage level, the parts per million, parts per billion, or parts per trillion? For all, of course, all of that is going to affect our sample preparation and any pre-concentration steps. Also, it will affect our detector as well, so how sensitive that detector is that we're choosing. Are we sure? Do we know what the concentration of the analytes are? If it's a complete unknown, again, we'd have to be thinking about setting up a very generic system that maybe can go to high temperature, but also as well, if it is a very high concentration sample, choosing the parameters to make sure that we don't overload our GC system, which of course can lead to contamination and lots of maintenance before we can use it again. So if we're not too sure either what's in there or what concentration the analytes are, or even the matrix, then again we need to be thinking about that when we first select our system. So if it's quite a low concentration, is pre-concentration required? And can this be automated on this instrument if we've got lots and lots of samples? So our problem analytes are the things that I term light thermally labile compounds. So these decompose in the hot system. Ideally, when we're setting up our GC or GCMS method, we want to be analysing and seeing in our detector exactly what we started with originally in the sample. So therefore, if we do have compounds that are thermally labile, then again, we want to be choosing the techniques to try and reduce the thermal breakdown of our components. So we'll look at that in more detail later. High molecular weight analytes. So I just mentioned just now that I've analysed, I've set up methods which is just still being used with molecular weight up to around about 1200, and these are subject to discrimination due to the low volatility. So again, if we've got these high molecular weight compounds, we want to get through all of the molecules of those compounds towards the detector without losing any en route due to mass discrimination. Other problem compounds are things like trace analytes, particularly in dirty samples, because these are much more difficult to detect. So we want to be selecting very sensitive parts of our method. But again, if we don't quite know what the concentration is, if we set up our system to be very, very sensitive, then of course we could potentially overload and contaminate our whole system, causing lots and lots of maintenance. Other problem analytes are things like active compounds. So these could be irreversibly absorbed or broken down in various stages of our system. So again, starting thinking about our GC system to start with, it could be actually in the sample introduction stage, it could be in the separation of the analytes, or it could even be in the detection stage as well. So active analytes, again, we need to be thinking about. So problem compounds just need more care when choosing and optimizing our analytical system. And we'll be thinking about that later on in that presentation when we're actually selecting the techniques that we'll use for each part of our instrument. So, researching and planning. So every method and every starting place, really we need to spend a bit of time just researching and planning our method development. So first of all, we could find methods from publications or instrument manufacturers' application notes. So column and instrument manufacturers are very good places to look because they're trying to show off their instrument or their consumable items, so for that particular application. They're always a good place to start. And of course, it may not always be the manufacturer that you use for your instruments itself. It could be other manufacturers. Only use these areas as a starting point, because often methods are not fully optimized, especially I tend to find in publications, because a lot of the time people make do with what they've got. And you might have a whole range of instrumentation, some of which may be much, much better for your application. So use them as a starting point, use them as a guide to give you ideas, really, of actually how to go about it. Now, I always go and draw up a plan of which techniques to try and in which order, and also once I've chosen my techniques, the parameters for each part of the instrument to optimize, and again, in which order. The reason behind drawing up a plan is that, especially if you're developing a method over time, alongside much of your other work, you can forget where you've got to. You can get lost, particularly for very difficult applications. So if you've drawn up a plan and then you've updated your plan as you've gone along, maybe use a highlighter pen to actually highlight areas that you've tried, ticks, make some notes, etc., then it means that if you're to go away on holiday and to come back, or you get pulled away on a different project, then you can very quickly catch up to where you were without having to go through the data files of all the research that you've actually done and the different parameters and techniques that you've actually tried. So draw up a plan. I just tend to take an A4 or maybe even A3 piece of paper, draw it all up on there, and then that can really aid you with your development, particularly over time. Also, when you get your method kind of almost finished and you suddenly encounter problems maybe with a particular matrix that you're using and you haven't actually tried before, then again you can go back and review your plan and see if there's anywhere that you can possibly tweak or improve on if you don't quite get the robustness that you needed for your particular method. So first of all, let's just do a quick overview of our GC instrumentation. So first of all, we've got a carrier gas. So that is turned on all of the time through our instrument, particularly we've got a mass selective detector at the end of it. So that could be sourced from either a gas cylinder or from a generator. So things that we need to think about are things like purity and also maintaining the purity of that particular carrier gas. There's various different carrier gases that we could use. So we'll have a brief look at that in a minute. So as I mentioned, when we do choose our carrier gas, we think about keeping that purity, because that, especially if we have a very, very sensitive instrument set up, we want to go and buy our very high purity of gas, and we want to maintain that purity into the instrument. So for example, I do a lot of GC times GC, and when I first started doing that in 2001, I did quite a bit of looking at different purities of carrier gas to see actually what it really improved my results. And I ended up using a purity of helium of 6.0, which actually reduced a lot of my noise actually in the baseline when I was using GC times GC. So it really, especially if you've got a very sensitive instrument, it could really affect it. And when we're thinking about sensitivity, there's two parts to that. There's signal and there's noise. So we always want to enhance our signal, but at the same time, we want to think about reducing our noise to get our best signal to noise level. So therefore, high purity carrier gas is one of those ways of reducing our noise, depending on the type of detector we're actually using, whether it's a GC detector or a mass selective detector. So then we want to think about introducing our sample, any sample preparation. We want to think about how we're going to vaporize that sample, or how we're actually going to transfer the sample from the autosampler onto the analytical column. So there's various different techniques. We also want to think about the column itself. So there's various different stationary phases out there. So we want to select a column that's going to be giving us the best separation at the lowest temperature. And then, of course, there's the detector or the mass selective detector. So various different parts to that. There's the ionization technique. There's the ionization technique. There's the mass analyzer, how we're going to separate the mass to charge ratios. And then, of course, there's a detector as well. And finally, we want to think about our data acquisition and data analysis software. So Data analysis software is something that we do need to optimize as well. And I tend to find that when you are developing a method for a long-term use where it's going to run at hundreds, if not thousands of samples over time, then you need to be spending an equal amount of time optimizing your data analysis parameters as you do the rest of your GCMS method. Because if you want to get your integration, quantitation as automated as possible, then you need to spend time optimizing those parameters. Quite often nowadays, you can spend far more time analyzing your data than you do actually preparing and analyzing your sample on your GCMS instrument. So these are all different various parts that we need to be thinking about. So thinking about our plan now, we can divide this up into various different stages. So first of all, thinking about the sampler. So the type of sampling, any sample preparation, packing materials, conditioning. So, for example, we could be doing headspace analysis, we could be doing SPEME, we could be doing SPE. So all of those are going to think about actually, can we automate it to our GCMS system first of all? If we are doing it offline, again, optimizing all the different parameters of that. And if we are doing it online, connected to our GCMS instrument, making sure that it works, because of course that sampler may be from a different manufacturer than the rest of our GCMS equipment. So then below that we've got our individual parameters for that. So thinking about things like sample volume, any flows, any timings, any temperature, injection volume, if it's something like headspace, any splits, purges, etc. And these sorts of parameters are very, very dependent on which type of sample preparation or sampling technique we've chosen to use for our particular application. The next stage to think about actually is our GC inlet. So again, the type of inlet we're going to be using, the technique that we're going to be using, on column, split, splitless, hot or cold injection, large volume injection. And when we've selected our technique, we need to be making sure that we select the correct liner style for the technique and also for the sample and the volume that we're injecting. When we then get down to the individual parameters for that particular part of the method, we're going to think about the temperature. The temperature of our inlet is particularly important if we've got high matrix loading or we've got if we've got thermally labile compounds. So ideally, we want to select the temperature to make sure that our least volatile compound is properly vaporized and transferred onto the column. But we're going to minimize the vaporization of any sample matrix. We're keeping the involatile material back in the inlet liner. And again, depending on the technique, split flows, split as time, if we need to use a gas saver, all of these are things about in our inlet. Then moving on to our GC oven. So thinking about our GC oven, we could think about carrier gas type. I've just popped it into this section, or it could be in your own separate section if you wanted to. Your column phase type and dimensions. Do you need to do backflushing? Backflushing is very, very easy to do these days with current technology out there on our GC equipment. So therefore, by employing backflushing, you can keep the rest of our instrument nice and clean, meaning lower maintenance. And again, we've got our individual parameters actually in our column oven. So we've got our column pressure or flow, so our flow of gas to that column to provide the best separation. We've got our oven initial temperature, ramp rate, and final temperature. And then we're thinking about our detector. So I've put detector in here because we're talking about mass spectrometers today, but you could be splitting to a different GC detector, for example, a flame ionization detector, an electron capture detector, and that can give us very useful additional information on top of what we get out of our mass spectrometer. So again, if you've got a number of instruments in your laboratory, it's which one is going to give you the best data for your particular application. So the type of mass selective detector, what type of ionization technique you're going to use. And again, then we've got things which are associated with our detector, so temperatures, transfer line temperature, and also what's going to go through the transfer line. Is it your analytical column, or are you going to use deactivated fused silica? Acquisition rate, mass range, gas flows, etc. So there's a lot of parameters again then you'd be choosing for your particular instrument. And finally there, I just mentioned before, the data analysis part of it. You could be using the standard manufacturer's data analysis that came with your instrument, or you could be using a third-party supplier. But what you're going to be thinking about is, does it give you the best integration, a very good automated integration? Can you do everything else that you want to? And can you get the report out that you need to? So the number of times that I see people printing out some results and then typing it into a different type of reporting software, that takes time. So, can you quantitatively move things across? Can you get the report out in the fashion that you want to? Because all of these take time. So these are the types of things that you need to be thinking about. So you can draw up a plan which is suitable for your application, that is suitable for the instrument that you have chosen to use. And then once you've drawn up this plan and put in every parameter that you can think of, then you can start thinking through how to develop that method, how to optimize each parameter, and also which order to optimize each parameter in, as we're going to talk about in a minute. So, first of all, minimizing our parameters, because from your plan you'll see a huge number of parameters that you could or possibly could go through and optimize. So first of all, start simply. Try and obtain standards of at least some of your compounds, and from the front end of your chromatogram, the most volatile compounds and the least volatile compounds, and then something in between as well. So try to obtain a standard to optimize your sample introduction, your column chromatography, and your detector parameters. So a very good way to do it is to obtain a reference chromatogram. So this could be an on-column injection is by far the best, because if you do an on-column injection, you're ignoring the sample introduction, and if it's a standard, you can be ignoring the sample preparation as well. So that means that you've just got the components that you want to be analysing. You can see if there's going to be a problem with mass discrimination once you get to that stage of optimization. So, for example, if you see that when you start optimizing, for example, in sample introduction, if the back end starts dropping off, you can then compare it to your reference chromatogram and see that's dropping off, that you are getting mass discrimination somewhere. So taking a reference chromatogram can be quite useful, especially if you're doing things like large volume injection as well. Expand your instrumentation to develop your inlet and your sampling methods. So you're really working backwards, but you're not fully optimizing each part of your method until you've got the method as a whole, really. So once you're happy that you can see most things at or everything at a reasonably high concentration, you can then start reducing your concentrations, and you can start tweaking the rest of the method to ensure each of your parameters are optimized, and then test robustness of your method and with samples, and check for things like carryover, etc. as well, and for sensitivity that you actually need. But start simply first of all, so try to obtain standards, because you can then really concentrate on sample introduction, your separation on your GC column, and also the detector, and then worry about real samples and sample preparation later on. So here we're going to go through a number of different stages, which I usually start with. So first of all, Analyte Identification. So first of all, you'll choose your instrument starting point. So you've got a lot of information you can get from this from your research, but also there's quite a lot of rules of thumb as well, which can give you a good starting place. So choose your carrier gas, choose your column, choose your inlet type and your method, your detector, injection, and all associated parameters. And first of all, you'll run your first injection and identify all of your compounds. So make a note of your attention time. So really you can't go on further to optimizing individual parameters until you can actually see where those particular compounds are going to be eluted. It could be the case that you've got complete coelutions of some compounds. So first of all, you need to do some tweaking to see these, or you may need to go and get individual standards of those compounds and run them just by themselves, so then you can see whether or not you can see them, and therefore if they would be coeluting completely to other compounds. So you want to really then at this stage be Working in identification, you may need a reasonably high concentration, especially if it's going to be a very sensitive method. So there's no point in thinking about optimizing for sensitivity, employing things like SIMs, the selective ion monitoring methods, if you can't see all of your compounds. You need to know where they are. To work on your column separation, to see all of your analytes, you're starting to get that separation on there. So you tend to be doing this with a reasonably high concentration standard to start with. You need to find where all of your compounds are. And also then at this stage you can start to identify those difficult, those problem compounds. So those ones which aren't giving you the sensitivity that you require maybe. Those ones that are coeluting, and also again things like isomers of each other, which are much more difficult to separate. Now the concentrations, how high a concentration of that standard really depends on the setup you've got. So for example, if you're using a very sensitive mass spectrometer, then it'll be, not be as high a concentration as others. If you're not sure, go into the kind of part per million sort of level to maybe a 1 microliter injection, and then you could go through and see if you can see something. If you think it's too high a concentration, the best thing to do is to start off with a split injection, so you're not getting all of that standing onto your column, and therefore you're not going to be contaminating your system. And of course, if you don't see anything, then you can either reduce your split ratio, or you can go to a splitless injection. And if you're going to be doing on-column injection, again, maybe think about going to a much lower concentration that you think you can see, maybe, to start with, and then you can increase the concentration to then be able to see those analytes. So, just go for a 10 times higher or something like that if you're not seeing everything. So it's always best to go too dilute to start with, where you're not getting quite enough on the column to see everything, because then you're not going to be contaminating your system. So you've seen all of your analytes, you've identified where they are, you can now start optimizing your parameters. The aims of this stage is to improve your sensitivity, because of course you might go to a quite low concentration actually when you're analysing your real samples, but also what you're doing in this stage is making your method robust. So this is a very important stage. So only ever change one parameter at a time, because if you see a dramatic reduction or improvement, you may not know which parameter has caused that. If there's no difference, quite often it's useful to go back to the original value and then move on to the next parameter. So for example, if you increase a particular temperature and you don't see any improvement, it's always much better to try and work at lower temperatures, particularly if you've got thermally labile compounds. If you have time, try a couple of injections at each value, especially if you're not sure if the results are true. So do some replicates. Start with large changes in value, then narrow down. So for example, maybe you're optimizing your inlet temperature. So for example, you could go for 300 and then drop it down and try 250 and see if there's any change. If there's no change, then 250 is better. Then you drop down again to 200, see any change there. So if it's between 300 and 250, next try 275 degrees C and so on. Now, one of the reasons why I drop it down the temperature is because then you haven't got the carryover to the next injection. Think about the order of change. For example, inlet temperatures start higher and then go to lower because you're less likely to carry over to correct your results. Because if you've increased it, you could have some carryover from a previous injection. So for example, it didn't get vaporized and didn't get flushed, and therefore you suddenly get a larger increase in the area count. And that could be because you've got this carryover. The next thing then, you've tweaked, you've optimized your method, you've optimized all those parameters. The next thing to think about is your calibration and limits of detection. So check your calibration curve. So go down, and what you always need to remember is when you're doing a calibration curve is that your lowest standard needs to be at or lower than your lowest concentration sample. The point at the highest concentration should always be at or higher than the highest concentration you want to be analysing your sample. So basically, you're bracketing your top and bottom standards around the levels of concentration that you want to be analysing for. Because you have no idea if your calibration curve is going to be linear above or below that curve. 120 to 30 injections is the same standard or sample and checks for repeatability. So what you're doing is checking for robustness. If you're doing this on a standard and you don't see a very good repeatability, then of course what's going to happen with your samples? Then it's not going to be as good as again. So you want to be checking those things with standards and then moving on to samples. If you find there's a problem at any of these stages, you need to be going back and fixing it. Because when you go to your real samples, especially very dirty real samples, these problems will only get worse. So if you don't have very good repeatability, determine the cause of it. Is it injection technique? Maybe you have thermally labile compounds or high molecular weight compounds, and you're getting mass discrimination or breakdown in your inlet. So this would be a very good point to go back and say, well, maybe I need to do a cold injection. Maybe I need to be thinking about how to get the high molecular weight compounds onto the column in a much better way. Detector instability, or should an internal standard be used? What's the minimal detectable limit? So checking the sensitivity of your instrument, getting for standards, and then of course thinking about that for samples. Make any tweaks to your method to improve sensitivity if necessary. So this could include injecting a larger amount of sample, injecting a larger volume of sample. When you're doing sample preparation, maybe you're preparing it with a much larger amount of sample. Rather than half a litre of water, maybe you're going to a litre of water or something. Changing to a selected ion monitoring method. So there, think about improving the sensitivity of your detector. To think about how to improve that sensitivity. So your SIM method, of course, is your selected ion monitoring method. If you're using something like a quadrupole mass analyzer, then you can go from scan, which is less sensitive, into a SIM method, which is more sensitive, but it's only for target analysis. And then finally, we've got to the stage with standards. So you want to be now looking at your method for real samples. So interference with your chromatogram could be matrix interference in your real sample. You're also looking for things like overloading of some matrix compounds, tailing of matrix components, which then affects your analysis and being able to identify your compounds of interest. So you may need your oven ramp rate tweaking, or you could even get to the point where you actually need to change your column to get the separation and improve it further. But remember that your sample introduction method and your detection method is still going to remain unchanged. Final temperature and hold time. So you need to make sure that you remove any involatiles from the column before you do it in your next injection. Always use a minimum inlet temperature to try and reduce the less volatile compounds being transferred onto the column. Carry over your highest concentration sample, thinking about dilution. Also test reproducibility now between samples or batches. Think about how often you need to recalibrate, and you can only do that by analysing real samples. And also thinking about how often you need to do instrument maintenance. So if you're doing lots of dirty samples, you probably need to change your inlet liner much more often than if you've got clean samples. And that is very application dependent, but it also really depends on the types of samples that you are analysing and trying to identify those dirty samples before they actually get onto the column. So now let's just think about the individual parts of our GCMS method. What do we need to be thinking about? So how do I get my sample into the GC first of all? For gas phase samples, you could introduce these directly, either using a gas sampling loop or a gas-type syringe. Gas-type syringe is particularly useful if you're just starting to optimize your method and you want to do quick injections just to see if it works. Or you may need to concentrate your samples. For example, if you're working down in the parts per trillion levels with gas phase samples, then you will need to pre-concentrate. So things like thermal absorption is very good for that. Also, you can use things like SPME, so solid phase microextraction, and SBFE, so stir-bar absorptive extraction. If your sample is a liquid phase, if you're looking at volatile analytes, you could be using headspace, or either static or dynamic headspace, or you might be wanting to go even more sensitive and use Persian trap. However, Persian trap is not so good for high concentration samples because you will contaminate the system, which means it may need replumbing and take 2 weeks. Semi-volatile, so you could be again using SPME, SBSE, and again, think about, do you do headspace or immersion? Do you put your SPME fibre in the headspace above your sample, or actually put it directly into the liquid? And if you're looking at semi to low volatility analytes, things like liquid-liquid extraction, solid phase extraction, and again, are you using those for concentration, or for cleanup, or for both? If you've got solid phase samples, so these could either be analysing direct the solid itself, or you could dissolve the solid, or you could crush it. Volatile analytes, again, think about headspace purge and trap. Semi-volatiles, again, think about SPME, SBSE, but also thermal extraction by using a thermal desorption instrument, where you're heating the sample directly. Semi-volatile to low volatile analytes, things like pyrolysis, where we're then breaking from those bonds and releasing the more volatile analytes, and then again, liquid-liquid extraction and SPE as well. Questions you need to be asking: does the volatility of the analytes match the technique you're going to be using? Does your sample need matrix modification? For example, if you've got more polar compounds that you need to get out of a liquid matrix, then you'll need to do matrix modification. Do you need to normalize your sample? Do you have various different levels of salt or changes in pH, which again will affect the sample extraction, the analyte extraction technique? Do your analytes require derivatization? So are they to make them either less active or more volatile? Again, that very much depends on the analytes or the techniques you're actually using. And is analyte concentration required? Does your matrix need removing? Do you need to do sample cleanup? These are all things that you need to be thinking about in your sampling technique. Moving on to the GC itself then, how do I transport my sample through the GC? What type of carrier gas are you going to be using? Hydrogen, helium, nitrogen? And this can be very analyte or MSD dependent. If you're looking at more gases, then nitrogen might be a good carrier gas to use. If you're thinking things like particular mass spectrometers can only use helium, for example, you couldn't use hydrogen. And hydrogen can be a bit bad for certain compounds because they hydrogenate particular analytes. So again, thinking about which type of carrier gas to match your instrument, but also match the analytes that you want to be looking at. So we mentioned earlier the higher purity, the carrier gas you use, but again is detector dependent, you get lower limits of detection. Do you want to use constant flow, or do you want to use constant pressure? Do you want to be using a ramped flow or a ramped pressure? So when you're optimizing your flow rate, you want to, first of all, achieve the optimal resolution for the type of gas you're using and also the analytical column. So if we have a look just quickly at the Van Diemter curve here, and remind ourselves as a height equivalent to the theoretical plate, if we were using nitrogen, this sort of flow rate would be give us the optimal separation. Helium, it would be at this point here, give us the optimal separation, but we could slightly speed it up and still not get a massive drop in our efficiency. And with hydrogen, again, around here, first of all, we'd be using much faster flow rates to get the optimal efficiency, but we could go to a much higher flow rate still. So again, the point that we choose depends very much on the instrument and the application. So we want to maximize it: faster chromatography, shorter run times, less longitudinal diffusion. But we also want to be very wary of our MS vacuum. What is the pumping capacity of our mass spectrometer? Because we don't want to be going to too high a flow rate. That will then affect the vacuum, which in turn will very much affect the sensitivity of the mass spectrometer. Next stage, how do I transfer my sample onto the column? Inlet type, on column injection using a split or splitless injection, or using a programmable temperature vaporizer, which enables to do a hot or a cold injection, or also an on-column injection. So thermally labile compounds may be much better by doing a cold injection technique. So the injection technique is concentration dependent. If you have very high concentrations for analytes, split injection is better. But maybe want to possibly do split or splitless, or maybe splitless plus large volume injection. That relates back to the concentration of our analyte. Sample dependent, hot or cold or on column. How dirty is our matrix? Clean injections only for on column generally, and thermally labile analytes. Once we've then selected these, we select our inlet liner to match the technique, the analytes, and the injection volume. We optimize our temperature to transfer all of the target analytes into the column, but keeping all the matrix, or as much matrix as possible, within the liner. That reduces maintenance and also runtime. Septum needs to be matched to the temperature in the injection technique. Ferrules need to be matched to the inlet type and the vacuum presence. So we wouldn't use a graphite ferrule, especially on the transfer line, with a mass spectrometer at the end of it. And then, of course, we've got all the associated parameters with our techniques, things like split flows and splitters time. So when we're optimizing our splitters time, for example, if possible, we compare it to an on-column injection. So you can see on here, this is our reference chromatogram. We can see, first of all, the size of the peaks, but also the relative heights of those peaks. We could then gradually increase our splitters time or even reduce it. The rule of thumb for splitters time is 2 flushes of the inlet liner volume. So if we estimate our liner volume, divide it by the flow through the liner, which is equal to the column flow plus the split flow, and multiply that by 2, then that will give us an estimate of the splitters time. That's the maximum amount of splitters time we would use. So what we then do is we take that and we then start reducing it down. And we then plot our splitters time against our peak area. And what you don't want to be doing is going to the edge of the cliff, is what I put it. So therefore, splitters time round about here would be ideal, because if there's any slight changes in anything, then we won't get a big drop in our peak area. If we're over here and got slight changes, then we'll really be dropping in terms of the area and the sensitivity of the method. So we don't want to be on the cliff edge, we want to be back from the cliff edge, and that really helps improve the robustness of our method. How do I select my column? So the phase, things like terms like separates like, or polar separates polar, we want to be choosing the phase to match the analytes we are separating. However, if we don't know what our sample is, selecting a standard X5, so for example HP5, DB5, 30 media 0.25, is a good start. But don't forget that once you know what's in there, it might be possible to optimize it further to get the best separation of our analytes. Ensure the column maximum temperature matches the volatility of our analytes. No point in choosing a column that has a maximum temperature of 260 if we need an oven temperature of 350 to get our analytes through the analytical column. ID minimized, but with the capacity of the sample amount injected. So reducing internal diameter improves separation, but of course it also reduces capacity. The length of the column, minimized while attaining a good separation. So we need it long enough to separate all the analytes, but we don't want it too long that everything sits in there for too long and suffers from a lot of longitudinal diffusion. CL thickness. Thicker for volatiles, thinner for involatiles, but overall minimized because it increases your column bleed and also increases the mass transfer time, so basically increases band broadening. You may need to change your column type later in the method development if the resolution of the analytes and matrix is not possible, and don't be afraid to do that. Next thing is to think about is our oven temperature program. So the initial temperature rule of thumb is technique or volatile analyte dependent. So for example, if you're using splitters injection, you want to be doing 10 to 20 degrees below the boiling point of the solvent. You need it to be long enough for all the samples to be transferred into the column. Once all of your analytes are on the column, you then start ramping up your oven temperature. Isothermal or ramped temperature program. Keep your ramping nice as simple as possible, because if it's complicated, it takes a long time to optimize and also has lots of room for error. It may be better to get that good separation to change the column phase. Final temperature and time. So don't go above your maximum temperature of your column. Make sure it's hot enough to get your least volatile analytes off on the ramp if possible, and your involatile matrix to all get out of the column as well. So they again control that through the inlet temperature. And consider back flushing if it is a problem. Now moving on to the mass spectrometer. So we have things like the transfer line, the ion source, the mass analyzer and the detector, as well as optimizing for the vacuum system as well. So these are all things to think about. So how do you transfer the analytes onto reducing the mass spectrometer? So the mass spectrometer generally is under vacuum and the GC is at ambient. So some manufacturers have recommendations, so for example 40 degrees below the final oven temperature. It is a constant isothermal temperature, so it needs to be hot enough to prevent condensation and band broadening within the transfer line. But if it's very hot, if you have thermally labile compounds, they could be degraded actually in the transfer line. So you want to have it hot enough, but as low as possible. So at the end of the transfer line is a vacuum, so the required temperature is usually below the final oven temperature because you've got this vacuum pulling through your analytes as soon as they get into the transfer line. Consider the maximum isothermal temperature of your column because the transfer line is at a constant temperature. So if it's too high, it damages the column and bleeds directly into the mass spectrometer, which causes lots of dirtying, and a damaged column will also cause activity. You can use deactivated fused silica, that could be quite useful. And the standard temperature in most methods I see is around about 280 but of course that is column and application dependent. How will I analyze my analytes? So now we're moving into the mass spectrometer part of it. So the fragmentation pattern. The mass spectrum produced depends on the ionization technique used. So for example, EI, so electron ionization, generates library searchable fingerprints. This is very good for unknowns if you want to match it against a library. Also, of course, it could be used as interpreter to determine the structure if it's not present in the library itself. But it is a hard technique, and sometimes you don't see the molecular ion. It completely depends on the analytes you're looking at. So using softer ionization techniques, maybe positive chemical ionization or negative chemical ionization, depending on the analyte, can be very good for determining the molecular weight of that analyte. You can also go into MSMS. This is electron ionization generally, but also you can use other techniques. But this then adds another dimension of selectivity in the mass spec, so it's very good improving sensitivity for trace analytes in a complex matrix, but it is generally target analysis only, so we can't use it directly to identify unknowns. The first question then with ionization is it target analysis or is it identifying unknowns? Which mass analyzer is best? So I've selected a few different mass analyzers here. Unit mass gives us analytical resolution, so quadrupole is generally unit mass, gives us analytical resolution with deconvolution. So if you've got little peaks eluting underneath the matrix peaks, then you can use deconvolution to pull out the mass spectrum of those smaller peaks underneath. Scan mode, less sensitive, but it's good to identify unknowns. But if you are using selected ion monitoring or SIM, this is much more sensitive, but it can only be used for target analysis. A time of flight mass spectrometer gives us simultaneous acquisition, so it's not scanning, so we get full mass spectra, very good for identification. And we can either get two types really, so fast scanning, generally these are unit mass, but these are very good for narrow peaks, particularly if you're doing something like GC times GC. Or you could be using a high mass resolution time of flight, so this is good for accurate identification of analytes because you can get the exact masses of both the fragments but also the molecular ion. And again, these give us full mass spectra, so good for identifying targets but also for unknowns as well. And finally then, MSMS, that could be from a triple quad, a QTOF, an ion shock, etc. We can do SRM, so single reaction monitoring, multiple reaction monitoring for MRM, neutral loss scans, etc. And these are good for giving additional sensitivity and or resolution for targets. They can be operated in full scan though, to identify unknowns, but these will not give us a good spectra as if we're using just a single quad instrument for identifying unknowns. So what mass spectrometer parameters need optimizing? So first of all, thinking about our scan range, we need to minimize it. If we've got a scanning instrument, we need to minimize the scan range. So it needs to be wide enough to detect all the masses needed for the method, but as narrow as possible. So less steps equals faster scan cycle. So if you think here, if we're scanning, we've got all those individual steps, the wider the mass range, the more steps there are, and the longer that will take, so we won't get as many data points across the peak. So when we're thinking about optimizing our low mass, if we're too low, we'll see air, and we're too high, we don't see all the fragments needed to identify the compound. When we're thinking about the high mass, if it's too low, we're missing the molecular ion, But if it's too high, we get lots of data that we might not be using, and also it takes time to scan when it's not needed. So we need to be optimizing this for our application. So where possible, we want to try and avoid 44, which is CO2, 40, which is argon, 32 is oxygen, 28 is nitrogen, and 18, which is water. So these will give us a high background. Also, we want to try and avoid any column bleed and matrix ions for sim and quant methods as well. So we don't want to be using the same ions as are present in our column bleed or matrix where possible. And remember that scanning instruments, the larger the mass range, takes longer to scan, so you get less data points or less time on each mass, which will also affect sensitivity. Simultaneous acquisition instruments, the larger the mass range, just makes much larger data files. So I've talked about data points. Let's just examine this. So ideally, when if we're doing quantitative analysis, we want to be aiming for between 10 and 25 data points or scans across a peak to define it. If there's too few, integration of peaks not into a reproducible. So you can see this peak here, we've got 7 data points across the peak. And we can see we're not fully defining the outline of that peak. And if we were to integrate it and then to rerun it, and our data points are in a different place, we would get different areas. So if we see too few, though, we can't see peak correlations for analytical separation very well. But if we get too many, our sensitivity decreases as our noise increases. So we need to be aware of this. So it very much depends on the peak width from the GC and also the acquisition rate for the mass spec. So if our acquisition rate was at 5 cycles per second and our peak was 0.5 seconds wide, we would only get 2.5 data points across the peak. If our peak was 5 seconds wide, we'd be getting 25 data points across the peak. So these are things we need to be thinking about when we're developing our GC method, but also the mass spectrometer as well. As we can see here then, this is a variety of different acquisition rates affecting our peak shape. So here we can see at the top is 60 Hertz down to 1 Hertz at the bottom. And we can see that our peak is getting smaller and much broader, and the shape is not very, very well defined, and our signal to noise also tends to reduce as well. And correlations are much more difficult to spot and deconvolute. Also as well, the fewer data points we have across the peak, we also get this suffering from spectral tilting or spectral skewing. This only occurs in scanning instruments. So it's much apparent with fewer data points, and we can improve this by increasing the number of data points across the peak. So our mass spectrum will look different at the front end, to the middle, to the back end of our chromatogram. And this is called spectral steering. Unfortunately, we don't have time to discuss this further here. So optimizing our acquisition rate. The acquisition rate affects the number of data points across the peak. So we optimize for the method average peak width. If we're doing qualitative analysis, 20 to 20 data points across the peak is good. Quantitative really want to be going in for 15 to 25 to get the reproducible area amount. Different manufacturers and instruments use different ways to adjust it. So scanning instruments depends on the mass range, plus, for example, sampling time, how long we're allowing each of the masses to reach the detector, or how long it takes to fill the trap. For simultaneous acquisition instruments is usually spectra per second. So we set our acquisition rate. We don't have problems with spectral skewing because it's not a scanning instrument, but it does very, very much affect the sensitivity. So the lower the acquisition rate we have, the higher the sensitivity we get from the mass spectrometer. Also, some instruments that can affect the mass resolution as well. So by how do we optimize our acquisition rate? So we can only fully optimize it once our GC method is optimized. So for G separation adjusted, check our data points, and then we enter our scan range, and then we check our average peak width in seconds at the baseline. So essentially where we would be integrating that peak. So we find out in seconds the peak width at the baseline. We determine how many data points we want. For example, if we wanted 15 data points and our peak width is 3 seconds wide, that would then give us 5 scans per second we want to be aiming for when we're optimizing our mass spec method. We then adjust our sampling rate or interval or whatever other parameter the manufacturer has to then obtain that number of scans per second. There's also other parameters you could actually need to optimize to get better sensitivity. For example, here, on a scanning instrument, optimizing your high-low mass resolution. So it can be selected on some. It's affected by voltages on the mass analyzer. For example, a quadrupole, increasing our peak width from this line down to this bottom line here. So we're increasing our peak width, of course, makes our mass resolution lower, but it also makes our peak taller, so much more sensitive. So therefore, if we're doing a SIM method, optimizing that will give us better sensitivity. Again, these are a lot of manufacturer-specific applications. In terms of our MS temperatures then, most ion sources reach between 300 and 250 degrees, but most applications set around 230 degrees. So it needs to be high enough to prevent condensation of analytes in our ion source, but also minimal to reduce analyte degradation or reactions, especially the hydrogen as a carrier gas. EI temperatures tend to be 200 and 250. Positive chemicalization around about 300, negative chemical ionization around about 150 to reduce fragmentation. So these all need to be optimized, particularly if you're using chemical ionization. EI may be absolutely fine, the first thing you choose, but if you really want to properly optimize your method, then tweaking these temperatures is very, very useful. For example, it's been proven that using PAHs with GCMS analysis, you're analyzing those, by increasing your ion source temperature can actually improve the sensitivity of these particular compounds. Solvent delay. So if you're using mass spectrometry, you need to be putting in a solvent delay, otherwise you'll damage your filaments. So by turning off the solvent delay, basically while your solvent is going through your MS acquisition and data recording, while the solvent exits the column is very, very useful. So you can either optimize this experimentally, start with a longer delay and then reduce until you see the solvent tail. If the method's from a different detector, for an example, an FID, you can see approximately how long it takes. But also if your mass spec has an ion gauge, so you can see what the vacuum's doing. When the solvent's going through the mass spectrometer, the vacuum gets worse and then improves again once the solvent tail has gone through. Things like threshold values are also very important, and you need to be optimizing these to get the relevant masses. So for example, here we can see that our threshold is too high because we can not see our molecular ion down here. Also, if you are going and touching this mass spectrum, then you need to be able to see these isotopes in here, usually the carbon-13 isotope, which you can't see if your threshold value is too high. If you ever extract an ion and see your baseline is flat, then your threshold value is too high. And finally, your detector voltage. Always the last parameter to optimize, because quite often you see an increase in the size of the peak, but also the size of the noise, particularly if it is chemical noise. Most have a maximum of 2,000 to 3,000 volts, but this is instrument dependent. And some specify that by increasing 50 volts doubles your signal to noise, and that's a very good rule of thumb. But the higher the voltage, the lifetime of the detector is reduced because you're using up more electrons. So you can improve the sensitivity, but optimize your other parameters first. So if you compare it to a camera, increasing your detector voltage is really improving your digital zoom. So it's just what you're seeing, you're actually making bigger. But by optimizing the rest of your GCMS method, it's almost like this optical zoom, where you're pulling everything much closer towards you, so you can actually see it much clearer. So do everything else first, and detector voltage last. So just a few tips basically on your mass spectrometer optimization just finally in these last few slides. So always leak check before tuning, unless the software checks the leaks automatically, because otherwise all your voltage will be increased if you have got a leak. Tuning your method column flow GCMS spectrometers to get your best sensitivity and stability. So you should be doing this before you go and optimize your method, especially the final optimization steps. And consider your detector when optimizing the GC chromatography, especially in terms of things like peak width. Optimize the number of mass spec, number of cycles per second for your analyte peak width. It's very important to get the right number of data points across your peak, both for sensitivity and also to identify your analytes. And different instruments may have different tools to improve sensitivity further, like things like threshold values, signal smoothing, etc. Getting stuck. Don't give up. Take 2 steps back and think through your plan. So have a look at your plan, review your plan, discuss it with a colleague. And again, if you've written your plan in the first place and kept it up to date with what you've tried and where you've been, it means this is much, much easier. Don't be afraid to try something different, but don't do that too quickly. Don't jump around different column phases, etc. But when something's not working, things like your column phase, your injection technique, your sampling method, go back and think of trying something different. Make sure that you write notes. Keep track of what has been tried and the results, and if necessary, seek outside help. Now, first question, this is just a review of all the different techniques that we've got related with gas chromatography, but this is just, to be honest, this is some of them. It's not every sort of thing in there. First, we'll be thinking about your sample, your analytes, your carrier gas, your sampling technique, sample introduction method, your column separation, and also your detector as well. So, but the first question you always need to be asking yourself is, what are you trying to achieve? Why are you analysing this sample? And that will then help you with the whole of your method development. Thank you. And do you have any other questions?
Well, thank you, Diane, for that excellent presentation. As Diane said, we now have time for a few of your questions. So, Diane, the first question that we have for you is, if my analytes are thermally labile, where would I start with setting up the method?
Okay, so if your analytes are thermally labile, first of all, you want to be trying to do everything at the lowest temperature possible. So, for example, I think we very briefly mentioned things like sample introduction techniques. Cold injection. So you can do cold injection either as an on-column injection or using a programmable temperature vaporizer. And if you're using a PTV, what you do is you inject your sample below the boiling point of the solvent and then heat up your inlet. And of course then, when you heat up your inlet, your analytes are vaporizing at the temperature they want to vaporize at, so they're less likely to break down. And again then, when you're doing your oven separation, you have to be gently heating up your oven to do the separation, not hitting it with a very, very high temperature there. And then finally then in your transfer line of between your GC and your mass spec, again you need to be minimizing that so you don't get thermal degradation there. So just basically each stage of your GCMS method, you need to be working to the lowest temperatures possible, but of course they still need to be hot enough that you're not getting condensation of your less volatile analytes.
Okay, Diane, and the next question is, how do I obtain a reference chromatogram if I don't have an on-column inlet?
Okay, obtaining a reference chromatogram, so this could be, for example, doing a split injection, you're doing a high concentration, and a split injection, it's only the split ratio which affects sensitivity, which will affect actually some of the main parameter actually in there. Now, you could actually go and do an on-column injection without having an on-column inlet, and quite often I do this if I need a sort of reference chromatogram, but where I want to just see the relative ratios and relative heights of the peaks rather than actually the concentration. And you can just do this just by taking the end of your column out of your inlet, so setting up your instrument to go but without an autosampler, quickly take the end of your column out of your inlet, dip it into your liquid sample, and then take it out, pop it back in again, tighten up the nut, and then pressing start. And that's a really, really quick and easy way of doing an on-column injection. Myself, I actually do an on-column injection manually, just using a syringe, and can quite accurately do a 1 microliter injection on-column just using a syringe, which just takes a little while just to actually optimize that.
Okay, and a couple of fundamental questions here, Diane. Could you remind everyone what a SIM method is?
A SIM method. So SIM method is a selected ion monitoring method. So this is actually usually in a single quadrupole instrument. So this is where we're now changing the voltages in the mass analyzer to only allow the mass to charge ratios through to the detector for the compounds that we're interested in. So for example, for each compound we could be choosing between 1 and 4 key ions in the mass spectrum, and then just changing the mass analyzer to only allow those through. So we're not seeing a full mass spectrum for that peak, but what we are doing is we're greatly improving the sensitivity of our method, because of course the less ions that we're looking for, the longer we can allow those ions through the detector, the more ions reach the detector for each mass, so hence the improvement in sensitivity.
Okay, and the second sort of fundamental question is, could you describe briefly what SBSE, stir-bar sorted extraction, is?
So stir-bar sorted extraction. So this is where we take, for example, a little stir-bar that you use for mixing your chemicals in a beaker, for example. So it's one of those little stir-bars, the magnetic stir-bar, and it's coated with a particular phase. The most common phase is PDMS. And what you do is you can take that, you condition it first of all, and then you can either place it in the headspace above your sample or directly in the sample itself. So, for example, if you're analysing yogurt, it's very difficult to extract the compounds of interest. So what you do is pop that directly into the yogurt, you stir it for like about 16 hours, for example. You take it out, rinse it with distilled water, and then the analytes are then thermally extracted. So what happens is it's heated. The analytes then gradually come out of the stir bar. They're then trapped, usually in the GC inlet, but that's at very, very cold temperature. It then traps and concentrates the analytes, which gradually come out of the stir bar. Usually takes about 10 minutes for them to come out. Traps in there, and then the inlet's heated, and of course then analytes are transferred actually onto the column.
Okay, and I think the final question today, Diane, is I don't quite understand how to optimize the inlet temperature. You mentioned starting high and then reducing the temperature. Why is that?
Okay, so when you're optimizing the inlet temperature, if you gradually increase it, of course, you're going to get more and more of your analytes transferring onto the column. So if you do one injection, say it's 200 degrees, then you might get all of your volatiles transferred across, but not so many of your less volatile compounds. And of course, what happens, those less volatile compounds are probably sitting still in the inlet liner. So now you can see, comparing your chromatogram against your reference chromatogram, that you're getting mass discrimination towards the end of your chromatogram. So you need to heat the inlet up higher to vaporize those less volatile compounds. So now maybe you go up to 250 degrees, you add 50 degrees on, and you do another injection. And suddenly you see these less volatile compounds suddenly get much higher in terms of their size, maybe even higher than your reference chromatogram. And that's because the increase in temperature not only has transferred the less volatile compounds from that injection, but also the previous injection. So you've almost got a much larger increase than you're actually expecting. So if you then start off at a high temperature and gradually reduce it and see if there's any change, you're much better because you're not getting a carryover from the previous injection. So, for example, you can start at 300 degrees, see if it compare it against your reference chromatogram, make sure everything's been transferred. If that's yes, then you reduce it down to, say, 250 and check it against your reference chromatogram. Have you lost those less volatile compounds? If you have, then of course, then it will be somewhere in between those two temperatures. And then maybe you go to 275, again, compare it against your reference chromatogram and so on. Or you could just plot the area of those peaks against the temperature, and then we'd see the increase and the sort of profile that was actually on one of the previous slides.
Well, Diane, once again, thank you very much for that presentation. If any other questions do come in, or if any questions haven't been answered, I'm sure Diane would be happy to respond to them via email. Thank you also to our scientific partners in this webinar, being Analyte Technologies, for their technical input and support.